Welcome back. As we have just seen in the last lecture, moving charges can produce a magnetic field. We saw that when we had a current, it produced a magnetic field, and that when we made the current into a loop, we could make an electromagnet. Also, we found out that a constant magnetic field could deflect a moving charge. The tricky part there is figuring out the direction that the moving charge is deflected. Okay, but how can we turn a magnetic field into a current? Well, if the magnetic field is constant, it will deflect a charge, but it doesn't seem to help us create a current. But that is if the magnetic field is constant. What happens when we have a changing magnetic field? Changing magnetic fields can create electricity. So we have two laws to learn about this. The first is Faraday's law, which tells us the magnitude of the current produced by a changing magnetic field, and then we have Lenz's law, which tells us the direction of the current. Kind of like our last unit, the magnitude of the current is usually not the difficult part. You can kind of find the numbers and plug them in to find the current. The hard part is finding the direction of the current. That's the part that tends to challenge people. So the direction of the current is determined by Lenz's law, and the amount of current is found by Faraday's law. Okay, so the concept was first discovered by Michael Faraday. So he set up a current that loops around a piece of iron and then returned to his battery. Next to this, he put a secondary coil that was also connected to a piece of iron and then connected it to an ammeter, which is a device that measures the current. The idea is that the first coil is an electromagnet, and he wanted to know if you could make electricity with a magnetic field. Well, he set this up and flipped the switch, and for a split second he thought it worked. The ammeter, which measures the amps, of course, flickered, showing current. But then it almost immediately went away. So when he turned it off, the ammeter turned on again, and then returned again to showing no current. So it seemed like it was kind of working, but not really. But after some figuring out, Faraday figured out that in order to produce a current, it requires a changing magnetic field. So a constant field doesn't do anything, but a changing magnetic field does indeed produce a current. In order to quantify the amount of current produced by a changing magnetic field, we need to introduce a new concept, the magnetic flux. The magnetic flux is very similar to the electric flux that we used back when we were discussing Gauss's law. The electric flux was a measure of the number of field lines, the number of electric field lines that are moving through a surface. Well, here the magnetic flux is the same concept, but with magnetic fields. The magnetic flux, this green lantern symbol, phi here, is equal to the magnetic field times the area of the surface times the cosine of the magnetic field line and the line perpendicular to the surface. So if the magnetic field is perpendicular to the surface, then the angle is 0, so the cosine goes to 1, and the magnetic flux is at a maximum. If the magnetic field and the surface are parallel, then that angle goes to 90, and the flux goes to 0. The idea is that the vector, the line defined by a surface, is perpendicular to that surface, so then we are comparing the field direction to the line perpendicular to the surface with the magnetic field. It should make sense that if you want to catch as many magnetic field lines as possible so they go through the window, you want to align the field perpendicular to the surface. So if you're trying to catch as many rays as possible, you would want to lie flat, sort of perpendicular to the surface. So in most cases, you're trying to maximize the flux, so this angle will turn out to be 0, and the flux will become the magnetic field times the area, but we'll have some homework questions that may use a different angle. Okay, so now we can find a correlation between the magnetic flux and the voltage that's induced by the changing magnetic field. So we are looking at a loop of wire, or a coil of wire, and the magnitude of the voltage is equal to the number of loops in the coil times the change in the magnetic flux with time. So n is the number of loops in the coil. Also, we need the flux to change with time. That means that if we have a stationary magnet and a coil, then no current will be induced. We need the magnetic flux through the coil to change. So either the loop or the magnetic field needs to be moving. So the strength of the magnetic field could also be changing. The flux then depends on the strength of the magnetic field. So if we make the magnet stronger, then the voltage can be larger. If we increase the area of the loop, that will also increase the magnetic flux, so that too will increase the voltage. And if we move the magnet more rapidly, or the coil more rapidly, I guess, then the voltage will increase as well, because it's moving faster with time. So basically, the more the flux is changed, then the greater the voltage, and then also if you increase the number of loops, then the larger the voltage, although you could also think of this as a way of increasing the area. So you increase the area, then you increase the voltage. So in the case of Faraday's experiment, what happens is, as he turned the current on, the current goes from 0 to its top voltage, and we know from Ampere's law that the magnetic field is increasing. So the flux through that second loop is changing quite rapidly right when the battery is connected. However, when the current has been held on for a bit, the magnetic field becomes the same, so then there is no change in the magnetic flux. There is a flux, but it's not changing with time. So after that, the induced voltage goes to 0. Once the current is turned off in the first loop, then the flux through the second loop goes from some large value to 0, so that too means you have a large change in the flux, and a voltage is induced, and so the ammeter there will shift. So the key concept here is that a changing flux and a changing magnetic field can lead to a current, while a constant flux cannot. Also, anything that changes the change in flux over time, so the number of coils, the speed of the magnet, the field strength, or the area of the loop, all can change the voltage produced via induction. Okay, so you have a quick question to do, and next we're going to tackle Lenz's law. Good luck.